The DOT had a vision about utilizing mobile LiDAR because they understand that it's new technology that's coming out and they want to learn about it, they want to use it. There's been some really good discussions. Ted Knack put a good article up in the LiDAR News the other week talking about the adoption of mobile LiDAR within the DOTs and some of the barriers, impediments, some of the issues that we're dealing with. And a lot of it's on the DOT side, but it's also on the service provider side as well. So you kind of have to look at yourself before you start pointing fingers at what that vision is and how to put that vision into practice. And we'll kind of talk about that with this project here. So the DOT, their vision is it's all assets. They do what's called a roadway characteristics inventory. They do this annually, and they're collecting this data to make sure that they understand how the roads are built. It's one of those federally mandated programs so that they can get funding for the DOT to maintain their roads. And they have to understand what they own and where it is. So we're talking all assets, we're talking signs, stormwater infrastructure, pavement condition, and what the DOT wanted to do is they wanted to evaluate mobile LiDAR technology. So one of the things that we first talked to them about, of course, is, well, how much money do you have? Because, of course, we can survey it all and make sure it's survey grade, but is that real in the application of a roadway characteristics inventory? Where historically roadway characteristics inventory are mapping grade types of projects. They came out of the evolution of the DOTs where they came and they said, hey, we just need to know the distance along a road from a mile post, from a mile marker, or from an intersection, and that's good enough. We can find that sign, we can find that stretch of road. That was good enough back in the day, but now they're looking to obtain survey grade data so they can use it for multiple purposes throughout the DOT, roadway characteristics inventory just being one of those pieces. So some of the things they wanted to accomplish, they wanted to say, hey, if we're going to go ahead and do this, what other aspects of our operations can we satisfy while we do a project like this? So these are some of the other things: surveying, mapping, landscape architecture, environmental assets, all these different types of things that they could satisfy with one mobile LiDAR pass and supplement some of the field work that they've been doing in the fields. We talked to them about some of the ancillary products that could be generated with a mobile LiDAR pass. So looking at as-built roadways and facilities, doing some design, some conventional mapping such as planimetrics and different asset types. But how they can really use the data at the end of the day was really what they were trying to determine and what the mobile LiDAR afforded to them. So once the data was collected, once they paid for it, how many times could they leverage the data to really increase the value of it? So this project focused on the collection of mobile LiDAR along with right-of-way imagery. So you can see here on the left-hand side of the road, the left-hand side screenshot, we have a point cloud shown by intensity from the VMX 250, as well as the mobile video that goes along with it where you can see information about these structures. So we're looking at what's the METCD code of a sign, or what's the color of a stripe, things that you can't get directly from a point cloud on its own. So a typical life cycle of a roadway characteristics inventory project for the DOT involves data collection, data extraction, and what they wanted to do was do some more advanced analysis. They wanted to say, which assets should I work on today with the limited funding that I have? So they're using risk to prioritize which assets they should be working on. They develop a capital improvement plan with that, which means I'm going to spend my money here over the next 10, 15, 20 years. They design projects, they do the work, and then they're actually looking at the life cycle of these assets. So, when we build a road, let's say it's going to last 35 years. That's the pavement design, or that's the road design. It doesn't necessarily always last that way because it gets different types of traffic than it was designed for. It might get more traffic, and maybe the materials that it was built from weren't up to quality, or there was something different that is affecting the life cycle of a product. The concept is that this is a endless feedback loop where you're collecting data, extracting data, using that to develop plans and programs, and executing those plans and programs. So I'm sure we haven't seen a picture of the very first generation LiDAR that we had out there for stormwater infrastructure mapping, but this is our first mobile LiDAR vehicle. This is the first one that we actually used in production with the mobile mapping. We had a Q120 on this vehicle here, modified Soccer Mom Nissan Quest. And then we got into some of the more rigidly coupled types of units where we're doing pavement data collection along with LiDAR scanning, as well as roadway imaging, and bringing all of this back to the office to do the office processing. We also have some imaging vehicles that are collected independent of the LiDAR vehicles to give us a 6-camera view of the right-of-ways. Once again, depending on the technology that we use, is really based on the specifications for the project. So for the DOT, this RCI project involved the data, a smaller portion of that life cycle, the data collection, the extraction, the attribution of the data in a GIS, integration into the DOT's RCI database, and then, once again, that positive feedback loop of helping support their life cycle planning. The big component here is to understand at the end of the day that the DOT cannot handle a point cloud. They can't store it, they can't deal with it, they can't manipulate with it, but at the end of the day, they need to integrate it with their RCI, the roadway characteristics inventory, and they need to deliver a report to federal highways at the end of the day. So once again, as a service provider, we have to make sure that we're providing, even though we're collecting great data, tons of it, it's really cool looking, and it's really sexy, the stuff that we do, but at the end of the day, we got to deliver boring point vectors, point lines, polygon vectors, and spreadsheets at the end of the day to make sure that these guys can get the funding that they need to do their jobs at the end of the day. So once again, single platform, many sensors. This project involved right-of-way cameras, a pavement camera to get the pavement condition, mobile lidar, as well as roughness and rutting, and then at the end of the day, GIS integration. So we acquire the data, we post-process it, there's a calibration piece in here, and then there's a classification of that data before we deliver it, the final vectors to the clients. So this project, we had one study area that was a small area where the DOT was interested in looking at what they call the Caltrans specifications. So once again, Caltrans has written the book on mobile terrestrial lidar scanning and what the specifications are and how you adjust everything to the control to make sure that you're hitting those accuracies along the length of the project. So their goal was to identify a project area and hit a certain point density so that they had the fidelity within the data from a single platform and then evaluate the derivative products from that. So there was two standards. We got labeled with one standard, which was kind of like the less accurate standard. They threw our name up against it, but that's basically processing to a local base station or a local cores network. So we wanted to understand if we're going to really do a statewide project, how would we really control this data in order to make it affordable for the DOT? So they basically said, if we're going to use this Caltrans standard, how much would it cost per mile to apply that standard, and what does that mean in terms of final accuracies, absolute accuracies? And then we had this Earth-Eye standard where we were processing to either a local base station based on where the project was located, or to a local core station if the baseline to the core station was close enough to post-process against. So we're giving them the results based on those different processing methods. So the project that we collected for District 4 was across the southeast portion of Florida. So it's hard to see that you see up there were basically these yellow blobs that you see all the way up in the north, kind of along the eastern shore. There's a bunch of projects. Some of them were 5 to 6 miles. Some of them were about a mile or two. And they were located throughout the state, but they represented different types of roads. Some of them were local roads, some were interstate roads, some were arterials, just all different representations of the different types of DOT roads. So for the Caltrans standard, we saw a little bit of information about that just earlier, a couple presentations ago, where we have these validation points every 500 feet. You have transformation points every 1,500 feet, and this is their specification, and they give you basically a way to kind of lay out your ground control and your survey points and the transformation points. And then this other Earth-Eye standard that we just call, the cheaper standard, but I don't want to apply all that to our name, but like I said, we got our name added to this from the DOT. So the concept is you're traveling in both directions. We're using these tie planes to tie the data sets together from a relative perspective, and then we're processing the trajectory just against core stations or a local base station, depending on where we were. We're calculating a project-wide RMSE for each one of these, so we have control under each one of these sections as well that we can check it against. And then it's a cost-effective methodology for much larger projects, but as you can see for the horizontal and vertical specifications, not as detailed as we have to deliver to the DOTs. So when you collect this data, obviously we know where everything is, but we don't know what it is. So we go through a rigorous process of filtering the data to reduce the noise in the data. So you can have vehicles, other objects within the data. We're trying to get to this ground surface filter so that we can check the accuracies of the ground surface against control. And then we're also doing feature data extraction. So we're collecting the data and checking it against an METCD library and different types of data sets that are out there to assign these METCD codes. So once again, the operators have ways of selecting signs and objects based on their color, their shape, using the Trimble technology.